So in our last video, we talked about how you can see patterns in multiples of numbers, and we used the sieve of Eratosthenes. Here's another version of that sieve. You can find many versions online, which is better for your kids to work out on paper, right, than on the computer, so they can get a real slow, careful, thoughtful approach to this. Here, what I want you to notice is this right here. 1 is a unique number, so we do not consider it. And then we cross out all the multiples of 2 except 2, multiples of 3, and so on, and we get the prime numbers. And here's the list of prime numbers: 2, 3, 5, 7, 11, 13, and so on. What I want to talk about now is this 1 is a unique number business, and what exactly is the definition of prime. A prime number has exactly 2 factors. So for example, 7 is prime because the only factors of 7 are what? 1 and 7. Exactly 2 factors. Oh, and this is wrong. This should say a composite number. A composite number, that's the opposite of a prime number. A composite number has more than 2 factors, kind of the opposite. So for instance, if I look at the number 15, what are the factors of 15? Think about it for a second. Let's see, we got 1. 1 goes into 15. We got 3. 3 goes in. 5 goes in. Does 10 go into 15? No. 15. That's it. But definitely more than 2 factors, right? So that's the official definition of prime versus composite. A little bit better definition than our prime number is only divisible by 1 in itself. Pay attention to this exactly 2 factors business, and that will help you. What is 1 and why is it special? So think about 1. How many factors does it have? What goes into 1? Only the number 1 goes into the number 1. So it only has 1 factor. Just 1. Just the number 1. And so then is it prime? Nope. Prime has 2 factors. Is it composite? Nope. Composite number has more than 2 factors. So 1 is not prime and not composite. There you go. It's a special case. That's what they meant by a special case. So now that's going to allow us to look at some interesting things involving prime numbers. So this one is called Goldbach's conjecture. And you can read about it a little more in your textbook, but the key thing that we have here is every even integer greater than 2 is the sum of 2 prime numbers. And as you can see below, this conjecture is called a conjecture because it has not yet been proven. It is not proven, but it's been tested up to this gigantic number right here. So let's talk about Goldbach's conjecture. So Goldbach's conjecture says every even integer greater than 2 is the sum of 2 prime numbers. That takes some translating to figure out. So we're going to use the strategy of taking apart every part of this sentence until we understand it. So this part says every even integer. What are the even integers? That just means even numbers like 2, 4, 6, 8. Those are even integers. But then it says every even integer greater than 2. Oops, so not 2. Greater than 2. So 4, 6, 8, 10, 12. Those are all my even integers greater than 2. Is. So is means equals. The sums. What's the sum mean? Do you guys remember what sum means? Sum. That word. That means plus. Of 2 prime numbers. So it's saying that we want to add, sum means plus, we want to add 2 prime numbers together. So it's saying we can get one of these even integers, like let's say we want to get the even integer 12 by adding together two prime numbers. Sum means adding two prime numbers. So let's find two prime numbers. What are the prime numbers again? The prime numbers are not 1, 2, 3, 5, 7. Do you think you can find two that add up to 12? So take a sec, pause the video, and see if you can do it. One really helpful strategy as you work is to have a list of the prime numbers right next to you so that you can look and see if two of them add up to 12. Remember, you can't use the number 1, so 1 plus 11 would not work out. We need two of this list. It looks to me like 5, whoops, not 6, 5 plus 7 would work. Is that true? Yeah, it is. And Goldbach's conjecture is that that works for every number greater than 2, every whole number greater than 2. But it isn't proven. We don't know for sure if it's true. It's just been tested for really, really, really big numbers. So next I want to talk to you about Mersenne numbers and Mersenne primes. These are named after Martin Mersenne, who was a French monk in the 17th century. That was a long time ago. And I want to talk about how to use this formula and how to get it on your calculator. So if we look at this formula, m equals, that's 2 to the x minus 1 is what that formula is showing you. So for example, if I look over here, when x is 2, let's see if we can use the formula. So it's saying, instead of m to the 2x minus 1, where we see the x, we want to put a 2. So that means that we have m to the 2 to the second power minus 1. And you know 2 to the second power is 4, right? So we have 4 minus 1, which is 3. So right in here, we're going to fill this in with a 3 in our table. Now, is 3 prime or composite? 3 is prime. All right. Let's try putting in 3. Now here the work has been done out for us. 3 to the third power minus 1 is 8 minus 1, which is 7. 7 is a prime number. So look at what's going on. I put a prime number in, 3, and I get a prime number out, 7. Let's see what happens when I put in 4. 4 is not prime. 4 is composite because 4 is divisible by 2. And 2 and 4 and 1, lots of factors. So when I put 4 in, I get 2 to the fourth, which is 16, minus 1, which is 15, which is also not a prime number, it's composite. 15 is divisible by lots of things. All right, let's try out 5 together. So we're going to see what happens when we put x equals 5. And we can even use the calculator to try it out. So instead of x here, or 2, whatever number is there, we're going to put a 5 there. Now, at this point, you're probably thinking, I don't want to do 2 times 2 times 2 times 2 times 2, 5 of them. I want to do this on my calculator. So how do you get exponents on your calculator? On your calculator, you do 2, and then you'll have either an x to the y or y to the x key like that, or it looks like a caret on your calculator. And then you put the 5, and then you put equals. So 2 to the 5th is 32. So that we've got now 32, and don't forget, minus the 1. 32 minus 1 is 31. And 31, so here x is prime, right? 5 is a prime number. Over here, 31, prime or composite? It's prime. And so we see a pattern emerging here of when it's going to be prime and when it's going to come out composite. It looks like, from our pattern, it looks like when we put in a prime number, we get out a prime number. When we put in a composite, we get out a composite number. But it's not a guarantee. So let's take a look at what happens when we use the prime number 11. We get 2047, which looks like it's prime, but it's not. 2047 turns out to not be prime. How can you tell? So what you do is you take 2047 and you try to see if it's divisible by things we'll just try prime numbers. That's all you have to try. Is it divisible by 2? You don't even have to try on the calculator because it's not even. How about 3? It is not divisible by 3 because if you add the digits up, 4 plus 7 is 11, 12, 13, you get 13, not divisible by 3. So you see we can use some of our divisibility facts. It is not divisible by 5 because it doesn't end in 5 or 0. Now we start checking. Is it divisible by 7? No, I end up with a decimal. All right, so back to our number 2, 0, 4, 7. Is it divisible by 11? Divisible by 11? No, because we get a decimal. So keep trying. 2, 0, 4, 7. So try the next prime number after 11. The next one is 13. Is it divisible by 13? No. Now, by now you're thinking, I want to quit. I'm done checking. But you should keep checking. Let's see if it's divisible by, let's see, we were at 13, 14, 15 is not prime, 16, 17 is our next prime number. Not 17. How do you know when to stop? Well, look at the result I get here. You should not stop until you get results that are the size of numbers you already checked. So now let's try 2, 0, 4, 7. And I just tried dividing that by 17, right? So what's the next prime after 17? Let's see, 19. Nope. By now you probably want to give up, right? Don't give up. 2, 0, 4, 7 divided by 23. Look at that. 89. It's not prime. It is a composite number. So that's how you check if a number is prime or not. You have to keep going until your results get as small as the numbers you've already tried. All right? So now you know something about machine primes, which is that you are not guaranteed to get a prime number out. Most of the time when you put in a prime, you get a prime, but sometimes you don't. And in fact, there is no guaranteed formula that will always give you a prime number.